All right, so last time, when we were talking about integrality, R is commutative ring. One, and T is an R alpha. So I'll be precise about what I mean about this, in a moment. We say T and T is integral over R if T is a root of some monic polynomial. And monic means that the coefficient of the highest degree term is one. Say xn is Rn minus one, xn minus one x. So if you can find some t in this R algebra that's the root of this, then we say that t is an element that is integral over R. If every element of t is integral over R, we call this, we say that t is integral over R. So let me make clear what an R algebra is. T is a ring with one, equipped with a homomorphism let's say phi from R to T. And I want this homomorphism to do a couple of things. Number one, phi is a ring homomorphism. Two, phi is an R module homomorphism. And I didn't say that here, but I won't also say it's a ring that is a modular. And I want phi of R to be contained in the center of T. And the center of T is a subring T that's commutative. Does anybody know sort of what the prototype for this is? I mean, whenever you encounter a definition like this, somebody is trying to generalize something very familiar.
Matrices.
Right. So, n by n matrices over R, that's a ring with identity. Notice it's not commutative, n is at least two. This is a ring with one. And how would what do you suppose the homomorphism would be? Yeah, just the old diagonal thing, right? So p of x equal xi. Right. Okay. So also, right. Also, another good example is R is a domain, then, R is a domain and P is an overring, or more generally a ring contained, but this is what I'm gonna be thinking about with integrality. Question mark? Then P is an RL. And you can weaken this quite a bit. You can weaken domain and you can weaken overring to a more general ring containing R. So let's look at some examples here. So consider some the ordinary integers. Let's do something exotic here. T,
Sorry, are there good examples where R is not commutative? If we're not assuming R is.
oh, I'm sorry. I'm assuming that R is commutative, but not necessarily. Yeah, yeah. Okay, so here's a cool example. Let R be Z and let T be Z adjoined with square root, or 1 plus the square root of negative 19 over 2. You might know what's cool about that ring, by the way. It is actually Euclidean. But it's actually a PID that's not Euclidean. But that's just for fun. I claim that every element here is integral over Z. So let alpha be, let's say, M plus N times 1 plus radical 19 over 2. Anybody, of course, what you can do is you can just start taking powers of this, right? So maybe I'll be really naive, and maybe I'll really regret this, but alpha squared is going to be what? M squared plus the square of this, which is going to be n squared times that's going to be minus 18 plus 2 radical negative 2 radical negative 19 over 4. But notice both those things have a common factor of 2. So in other words, that's what you get when you square that, right? And then 2 times the product of the 2. So that would be Mn 1 plus radical P. Well, that's pretty terrible. It's kind of hard to tell what this is a root of, or even maybe we even have to go further. But there's actually an easier way to do things.
It's fine, the polynomial for the 1 plus root negative 19 over 2.
Well, right. Essentially, I'm going to do this a little bit more. Yeah, you could find the polynomial if you like, but another observation to make is complex numbers that are not real come in conjugate pairs. So the conjugate of this would be M plus M 1 plus, or I'm sorry, 1 minus radical 19. And so notice that when you add these two things, what happens when you add alpha and alpha bar? Well, I guess you get what, two m plus n, don't you? And what happens when you, multiply these? Well, it's not quite as bad as this, right? You get m squared. For multiplying these, and fortunately here, the conjugate comes out a lot nicer, right? So you get n squared times, I guess it's going to be what, 5? Right? This prop, this and this should be 5, be 20 over 4. And then 2 times, well, actually, we've got these middle terms, so we've also got an mn term. So it should be mn times this thing, and then mn times the conjugate. And when you add it to its conjugate, you get 1, so it should be just mn. So let me clean this up a little bit. Everybody okay so far? Now notice that so in this case, this is going to be x squared. Alpha plus alpha bar is going to be and then product of conjugates. So alpha, and in fact alpha bar as well, is a root of this. So any element of this ring is actually integral. Given your parameters m and n, notice that the coefficients here are integers and good to go. Right? Everybody okay with that?
Should we also say something about, okay, so we have these examples here, classic examples where T is an R algebra. Are we also claiming that this is a Z algebra?
Oh, yeah.
So is it true, like, for example, given any domain, you would join any algebraic element, and that's an R algebra?
Well, right, because in fact, if you have, in general, so let's address that question here. So in general, suppose you have, let's see what we need, as a matter of fact. Let's suppose notice that T is an R module, right? And it's a ring containing. And since T is commutative, right, that makes our life a little bit easier because now our homomorphism goes into the center, right? Because everything's the center of T. Right? And in the case where we have inclusion, then for all R and R, this is another good reason to take the identity to the identity, right? So the moral of the story is if you have an extension of commutative ring with identity, then that's an algebra. Algebras take really the more interesting ones are the ones where you have something non-commutative. This is where it generalizes.
even if T isn't commutative, because B preserves the commutativeness of R, it doesn't automatically go into the center.
Yeah, but why would you put that element of D with an element of R?
Yeah.
You don't know if it goes down.
Right, because it has to be in the center of the whole ring. So even though the image, even if this doesn't go,
Oh, I see.
yeah, so are you okay with that?
Yes, I.
All right, example. Um, Well, you that are in oversee. Let me first make an observation that's a little bit silly, but it's important to make. Note, if R equals T, then, well, let me not do it that way. It's a little more. Any element of R is integral over R. Right, and the polynomial is so X minus R, right? Okay, so if I look at everything that's integral over Z, that is also a rational number, I know that I get all of Z, right, at least. Do I get anything else? Is there any element of the rational numbers that's not an integer, but yet is integral over Z? No, there's not. Suppose A and B is in. And I want y'all to kind of see what happens here, because I think this sort of illustrates an important sort of thing about the way math works. Suppose that A over B is integral over C, right? Okay, before I get carried away here, what assumptions might be good for me to make?
A and B are relative.
Right, and I can do this here because A and B are integers. Okay. Since A and B are integers, we assume GCD of A is 1. Now, let's assume that since A over B is integral, A over B is the root of some monic polynomial Okay, so let's just get on the bulldozer and go. Let's just write down what this means, bro. Just shove in A over B for X. What might be a move in the game of chess now? I hate fractions, don't you? That will just make it a little bit easier if I can do that. So if I multiply both sides by b to the n,
Now what?
Now we can like pass A to the end to the other side and see that this side, the left side is divided by B, but the left side cannot be divided by B.
I think you want to get a little bit, stream that up a little bit. So let's suppose there exists a prime P, not zero, such that P divides A. So this equation here, certainly P divides zero, and P divides this chunk. So we must conclude that P divides A to the n. Right? But what do we know about primes? P divides A and P is prime. And what's the problem with that?
A and B were equal times.
So P divides A and P divides B, which is a contradiction. So what do we conclude from this?
No primes dividing.
No primes. Hence, no prime divides B. And what kind of elements have no prime divisors? So B equals plus or minus one. Therefore, A over B is an integer. Okay, so this is an equal example because it shows that everything that's rational and is also integral over Z is still in Z. But if you worked out this example for yourself, what do you suppose you should notice here?
More for you.
That is correct. That at the very least, this should work for every UFD. Where do we needed it? We needed it right here. To make sure that there weren't any factors in common. We needed this fact here that A had that prime, I'm sorry, right. We need the existence of primes here. Right, and of course, in a general UFD, we couldn't say B is plus or minus one, but we could say that B is a unit, and that's all it would mean. Right. Okay, any questions on that? Let me give you perhaps one more example here. Yeah, I want to do this. Consider this right here. So this is of all complex polynomials, but I demand that the constant term be just rational. Let's let T CX. Right? So this is all complex polynomials. Okay. Can anybody tell me what elements of, T are integral over R.
The R.
Well, let's try this. So let me can somebody give me an example of any element that's not here but is up here? And make it easy, because I've got.
Transcendental.
So like what?
I.
You were correct. I want a different example. Well, okay. how about I? Now, of course, I didn't take Pedro's example, I took Charlie's, because your example now would foil me in what I'm gonna do, but keep in mind that he asked for I, and let's look at what happens here. I claim I is not integral over, the bottom ring line. Certainly pi is an element of this, agree? Let's suppose it is, let's try to get a contradiction. Suppose pi is a root of, I wish I'd call it something else, but I'll do this. Tn plus, of each Rix in R. I put the X there to emphasize that these things are polynomials, right? And T is my variable. Okay. Now let's suppose that pi is the root of this. So what do we get? We get pi n plus Rn minus 1 x pi n minus 1 plus R1 x pi plus R0 x is equal to 0.
Now we can evaluate those polynomials on zero, and we get a contradiction, right?
Right, this is not super helpful yet, but if we make the observation, as you point out, consider phi from R into Q given by phi of R of x is R of 0. So that's my fancy way of saying, notice when you take any polynomial here, you plug in x equals 0, you get back into the rationals. And I'm going to apply that homomorphism to this equation here. And if I apply phi, I get this. And tell me what happened. What's the problem here?
Pi is nothing.
This implies, right, pi is algebraic over Q, which is the contradiction. Although I haven't proved this for you, I hope that you know the folklore that pi is a transcendental number. So, your example of pi is interesting because I produce a number that is in here, a constant in fact, so it's convenient, that's not here, right? His example would have worked, right? Because certainly I is algebraic over Q, so it's algebraic over that bigger ring, right? Anybody want to venture a guess as to what are elements of T algebraic over R? So if I could gather together all the algebraic elements, so if I could gather together all the elements in T that are algebraic over R, what are you supposed to look like? Yeah, certainly.
Polynomials with algebraic constants.
Okay, that's exactly right. This turns out to be,
In this case, the algebraic and the integrals all the same.
what's that mean?
In this case, the algebraic for P and the integral over R and the integral for R are the same.
No, because, you could have, so I know where you're going with this, right? Because you could theoretically take any constant term that you can make from R and turn it into a unit. But this isn't the field. For example, if you start the polynomial with X, you can't invert that. Right? So, now, from a practical point of view, I think that, what do you think here? So what you actually get is this thing right here. So you get algebraic elements. So what it means to be, so in other words, so from the perspective of, and maybe this is what you meant, from the perspective of, okay, so let me give you an example of something that's, well, from this ring, perhaps, so, for example, you could look at something like, well, actually, so here's what I'm struggling with, run your question by me again, because
Oh, I want to know if in this case, every algebraic was also integral.
So algebraic over what? So everything that's algebraic over this?
Yeah.
Is also integral over this? So everything that's, algebraic over R satisfies any, well, so
And how
if you stick to this, so for example, this is why I'm struggling with what your question is. If you look at this equation here, this could be construed as an algebraic equation, coefficients here, right? And the solution to this is -1 over X, certainly it's here, right? This is not a monic polynomial, and your 1 over X is never gonna, so I think that there's sort of not enough terminology we're using here. So if you look at 1 over X, that is certainly algebraic, over this, but it's not in there. And the problem is neither one of these things are fields in the first place. And when you talk about algebraic extensions, you usually assume that the bottom thing is the field. Now, what is true is, well, yeah, so that's really part of the problem here. Because you can have things like this. Okay, other questions? Okay, so let me give you, this is a huge theorem here. I don't need a lot of this theorem for a lot of the things I'm gonna apply it to, because I usually talk about over domains. But I'm gonna give you the whole shebang and explain to you why the whole shebang works. Let R be commutative, T and R algebra, U and T. See this. Let R be a commutative ring of 1, T and R algebra, and U an element of T. And basically, this theorem is going to, we're going to characterize when things are equivalent. The following are equivalent. Number 1, U is algebraic. I'm sorry, integral. U is integral over R. And two, there is a finitely generated R module. A contained in T, such that UA is contained in A. A, and the left annihilator of A and T is 0. Right. Now, so this condition, if you spend most of your life messing with domains like I did, this condition is not really needed so much, because the left annihilator of A and T, well, you'll see the way the proof builds up. If T is a domain containing it, then the left annihilator has to be. Well, let me hold this. Oh, yeah, it does. If this module is contained in T. Yeah, what I was saying is correct. Okay, so let's prove this. So for the forward direction, so let's suppose that we have that U is integral, and I want to find this finitely generated model. So, well, let's suppose that we have this minimal polynomial here. If U is integral, if U is integral over R, then U satisfies an equation that looks like this. U to the n plus Rn minus 1, Un minus 1, R1 U plus R0, 0, each Ri and R. Agree? That's what that means. So in this case, let A not T. So notice this is, of course, is contained in T because U is. So this is just modules generated by 1 and the powers of U up to n minus 1, right? Notice that UA is generated by U squared, U cubed, UN minus 1, UN. But UN is this mess, sort of. Right? And notice that the UN is redundant because we've already got this. So this is actually generated by U squared, UN minus 1, which is contained in A. So we've got that defeated.
We don't need one to put R0.
What's that now? Oh, you're right. Yeah, I missed that. Okay, now for the other bit about this left annihilator stuff, let me take you back to linear algebra a little bit. So I'm gonna use kind of a linear algebra result, which isn't too hard because I actually show it to 3110 people, but let's recall that if M is an n by n matrix, from some linear algebra, if M is an n by n matrix, and is the adjunct, or it can be called the classical adjoint. Adjoint, which is that transpose cofactor matrix with the appropriate signs in there. So okay, so then it turns out that M classical adjoint of M is determinant of M times IN. Where by IN I need the n by n identity matrix. Now suppose we have M. I just almost spread it over here. So suppose that we have M times the vector A1, A2, AT is equal to XA1 so I have this eigenvalue equation here. Then minus XIN times equal to the zero vector. And so when we multiply this by the classical adjoint of M minus Xi, we obtain determinant of M minus Xi times is equal to the zero vector. Okay. So now let us, okay, good. Let us tackle the other direction. The other direction is actually interesting because this is this module. So this reduces integrality, which is basically does this thing, is it a root of some monic polynomial, which could be hard to determine. It reduces it to like finding this finitely generated module. So let's suppose that A is equal to A1, A2, up to AN. Let's draw point brackets like that. And let's suppose that UA is contained in A. Now this containment here with UA contained in A, gives us, some equations. So A1, so what this means is when I hit, U times A1, this should still be an A, so it should be a linear combination of, this. So this should be R, let's say, 1J. And more generally, UAI is a linear combination. One R I J A J J is one. So we can write this. So of course, this is a system of equations here that we can write in matrix form, which we will. And in matrix form, we have this. U minus R11. R21, U minus R22, R23, R2N. All the way down to U, or no, RN1, RN2, N3, U minus RN. Times whatever I have this here, A1, 2, N is equal to 0. Right, because this is just this equation here with, I guess I've, so, yeah, I did turn this around, this is a sign everywhere. These should all be negatives. Well, the equation again. Right, because basically this is what you get when you bring this over here, right? You got U minus A1 minus R11. So everybody okay with this? Now, by our observation above, so the determinant annihilates it annihilates A1 up to AN. By our earlier observation. So the determinant is 0. Our matrix is 0. Right, the determinant, this has to be 0. But guess what? But that gives, if you work this out, anybody's ever worked out eigenvalues, this gives our mnemonic polynomial for you. With coefficients in R. Right, just working out that equation there. Okay, any questions? Right. So this determinant has to be 0, work this out, this gives you a mnemonic polynomial. I'm being sloppy here, but you know, the leading term will give you at the end, the coefficients for all in R. Yes.
For its direction, do we show that the annihilator of A is 0?
Yes, that's contained in here as well. See if you can. Yeah, so, well, I mean, look at the module that we got here. So the statement of the theorem says. Right, so for the forward direction, we just, yeah. I did say- Well, the left annihilator can. Oh, yeah, yeah, so look that over, we'll talk about that, refresh that question next time if you haven't solved it out, but yeah, it's. Okay, others? All right, well, we will see you all on Wednesday.